the two Legendre symbols when you're looking at a pair of primes. The law says that the Legendre symbol of one prime p modulo another one is equal to minus. It has the opposite status when you're looking at whether q is a residue modulo p. In the case where both primes are congruent to 3 mod 4. And otherwise, the two symbols are equal, meaning either both primes are quadratic residues modulo the other one, or they're both non-residues modulo the other. When they're both congruent to 3 mod 4, they take opposite states. Okay? And the otherwise means one or both of the primes are congruent to 1 modulo. Remember, all odd primes will be congruent to 1 or 3 mod 4. So in this one special case where they're both congruent to 3 mod 4, this is what quadratic reciprocity says, that the Legendre symbols take opposite value, but otherwise they take the same value. We've already seen an important application of this in to give you an algorithm to evaluate arbitrary Legendre symbols. And we're going to see a second application of it today, where it can be used to prove another couple of cases of Dirichlet's theorem, about there being an infinite number of primes in every arithmetic sequence, which isn't obviously a sequence of all composite numbers. But we are going to work towards the proof of the law of quadratic reciprocity, and the proof is in a section at the end of the chapter, but there's a couple of preparatory results that we need for it. Okay, and this is the first one, so we're just going to spend the first bit of this lecture talking about the first result, and then we'll look at the application. We'll get doing some more practical stuff, doing the application of quadratic reciprocity to that special cases of Dirichlet's theorem. Remember, the main result we have about evaluating the Legendre symbol is Euler's criterion. And that says for p and odd prime, and n, that the Legendre symbol n modulo p is congruent to this power of n modulo p, where you raise n to the power of p minus 1 over 2. N to the power of p minus 1, by Fermat's little theorem, that will always give you 1 modulo p, providing that p does not divide n. So when you're taking the square root of it, you're effectively taking the square root of 1 there, so you're going to get 1 or minus 1. And in the proof of Euler's criterion, we proved that if n was already a square, n was a quadratic residue, and you raise it to the power of minus 1, p minus 1 over 2, you're effectively raising the square root of n to the power of p minus 1, and so you're going to get plus 1. And in the case where it's a quadratic non-residue, where it is not the square of anything, then you get the other possibility, minus 1. Okay. And this result by Gauss can be seen as a kind of an extra step from this, just getting another way of looking at the relationship between the Legendre symbol n mod p and other properties of n compared to the modulus, other congruence type of properties of n. So we have this theorem 8.7 of Gauss. Now it looks kind of a bit odd when you first see it, but it's actually theorem 8.7 of Gauss. What it is, it's a generalization. The generalization of the argument we used to establish. We showed a result about the Legendre symbol of 2 modulo any prime. And that gave us, so the result about that told us that whether this was plus or minus 1. And it told us that it was +1 when p was congruent to ±1 modulo 8, and -1 when p was congruent to ±3 modulo 8. Sorry about the abbreviations there, just getting close to the edge of the board. The argument used to prove that, I'll just roll back to where we proved that. We looked at all, well, the way we described it was that we looked at all the even congruence classes modulo p, namely the congruence classes 2, 4, 6, 8, etc., all the way up to the even number p minus 1. And we analyzed the product of those carefully. We looked at the product of those very simply. First of all, it's simply 2 times all the numbers 1 up to p minus 1 over 2, 2 times each of them. That allowed us to take out this power of 2 to the power of p minus 1 over 2. Of course, you recognize as the right-hand side of Euler's criterion. You get this p minus 1 over 2 factorial. And then the other way we looked at it, on the way to proving this result, the other way we looked at it was we looked at all these powers. All these multiples of 2, all these even congruence classes, and we associated plus and minus signs with them in a way that allowed us to consider all of them as congruent to something from the first half of congruence classes. Plus or minus an s, where the s was 1, 2, 3, all the way up as far as p minus 1 over 2. So it's this very careful argument about multiplying together multiples of the number in question, multiplying together multiples of 2, and just being a very careful argument with what's going on with the plus and minus signs. That allowed us to establish this result about the Legendre symbol of 2 modulo. So theorem 8.7 is a generalization. So the proof is here written out in the notes. I just want to talk you through the main parts of it. It's a step along the way to proving our really important result of the quadratic reciprocity. So we're generalizing this argument from when we looked at 2 modulo p. So there we looked at multiplying together all the multiples of 2. So to generalize it then, when we're looking at an arbitrary case of n, we're going to multiply together all the multiples of n. Okay, just realize I haven't exactly stated what the result is. So the result is, so it's a way of evaluating the Legendre symbol n mod p. And he uses this number n. Now what's this number n? N is what you get when you consider all the multiples of n, all the way from 1 times n, 2 times n, all the way up as far as p minus 1 over 2 times n. You look at all those multiples of n, and you count how many of them have made it in to the second half of the congruence classes modulo n. Okay, so half of the congruence classes modulo n are greater than p over 2, and half of them are less than p over 2. Got p over 2, which is not an integer, of course. So you got p minus 1 over 2. There's another one on the list. P plus 1 over 2. P plus 3 over 2. This continues all the way up as far as p minus 1. This list of congruence classes modulo the odd prime p, this naturally splits up into 2 halves. The half that's less than p over 2 and the half that's greater than p over 2. So what Gauss's theorem says is that when you look at all the multiples of n modulo p, and you count how many of them land in here. So we look at every multiple of n all the way up as far as p minus 1 over 2. So we're only looking at p minus 1 over 2 multiples. We're taking all these numbers, multiplying them by n. Sometimes when you take the congruence class, sometimes they'll land in the second half of congruence classes, sometimes they'll land in the first. the count of how many land here, which is this number m, this is when you raise minus 1 to that power, you get the congruence class of n modulo p. So in other words, the congruence class of n modulo p just depends on whether this count m is odd or even. Okay? Because minus 1 to the power n will give you minus 1 if n is odd, plus 1 if n is even. Okay? Now this looks kind of a bit mysterious and a bit kind of hard to understand and process when you first see it, but the argument that leads to it is just a straight generalization of the one that gave us the Legendre symbol of 2 modulo. So we just attempt to copy that argument. So first of all, we just multiply together all of the multiples. So n times 2n times 3n, all the way up as far as p minus 1 over 2 times n. Multiplying n by each of these integers, and multiplying all those products together. Okay, so you can factorize the n out of each of these factors, and the total number of n's that you have is p minus 1 over 2. Okay, because you've looked at p minus 1 over 2 multiples of n. P minus 1 over 2 factors in the brackets. So you got n to the power of p minus 1 over 2, and the numbers that are left behind after you factor out the n is simply 1 times 2 times 3, all the way up as far as p minus 1 over 2. So that is our old friend p minus 1 over 2 factorial. Period again. Then we start to bring in this notion of counting how many have made it into the top half and how many are still here in the bottom half. Okay? So what we do is we consider a typical multiple, j times n, where j is one of the options from here, between 1 and p minus 1 over 2. This is going to have a standard residue modulo p called r. Okay? So the r is either going to be in this top half or in this bottom half. If the residue r lands in here, so we take a j from p minus 1 over 2. You look at the multiple j times n. This is congruent to r modulo p. And r might live in here, or it might live in here. Okay, we don't know. If the r lives in here, that means it's congruent to the negative of one of the ones from down here. Okay? So if r is one of the high congruence classes, we can consider that the negative of one of the lower congruence classes. Okay? Because everything up here is the negative of something down here. Okay? P minus 1 is the negative of 1. P minus 2 is the negative of 2, etc. Okay? So if this congruence class R is living in the second half, we choose to name it as, we choose to consider it as minus s, where the s comes from the first half. If the r lands in here, we just consider that a congruence class level. Okay. So what we get is that to each multiple j, we're associating basically a plus or a minus sign. If the j comes in here, the plus or minus sign, which we've named epsilon j, the plus or minus sign is minus 1. If the residue lives in here from jn, we're considering it as a plus 1. Okay? So that allows us to say that every multiple, or each multiple jn, is congruent to epsilon j, which is a plus or a minus sign, times sj. Where sj, s subscript j, this is the s associated to this j, where the sj always comes from the first half, okay? But it may be considered with a plus or a minus sign as it needs to be, considering whether this multiple of n lands up here, you get a minus sign to flip it down here, or if jn landed down here to begin with, it just takes a plus. Now, when you look at what's happened, actually, these SJs are all of the numbers from 1 to p minus 1 over 2. Okay? So we end up with a kind of one-to-one correspondence class between all the JNs. These are all the multiples j times n. And each of these is going to be congruent to one of these numbers down here. So these are all the congruence classes of 1, 2, 3, all the way up as far as p minus 1 over 2. So these are all the first half of the congruence classes, the early congruence classes. And they all carry a sign, a plus or a minus 1, according to whether the RJ landed up here, it gets a minus sign, we make it represented as a minus S. Or if it landed down there, we just call it S, whatever congruence class it landed at down here. Okay. And remember, the M we're trying to capture that's in the statement of the theorem is the number of congruence classes that landed up here. The number of multiples of these j times n that landed up here. So what we do then is we multiply together all these multiples again. Okay. So just as before, when you multiply together all these multiples, you've got n raised to the power of p minus 1 over 2 multiplied by the factorial of p minus 1 over 2. Okay? You've got 1 times 2 times 3 all the way up as far as p minus 1 over 2. And you've got n by n by n by n all the way up as far as p minus 1 over 2. So you've got n to the power of p minus 1 over 2. So again, we get this thing on the left, n to the power of p minus 1 over 2 times the factorial of p minus 1 over 2. But this is going to be congruent to multiplying together all of these congruence classes. And we consider them as the plus or minus Sj. So this is the plus or minus Sj, okay? But the S's all come from here. So this is just equal to, epsilon j times j. But when you're multiplying these all together, remember the epsilon bits are just plus or minus 1s. When you're multiplying together a load of plus and minus 1s, what it's equal to is just the number, is just all you have to focus on is the minus 1s. Okay? Because every time you plus 1 in a product, it doesn't change anything, so you can just forget about it. So you just have to look at the occasions where you had a minus 1 here. So you got a minus 1, and the count of the total number of factors of minus 1 you have here is this number n from the statement. The number of times the multiple j times n lands up here. And all the other factors that are in this big product is just you're multiplying together every j from j equals 1 to p minus 1 over 2. So that's exactly p minus 1 over 2 factorial once again. Again, just as we did when we considered the Legendre symbol 2 mod p, this factor here, p minus 1 over 2 factorial that you see on both sides, that can be cancelled from the congruence, okay? Because it's a number co-prime to m. It's co-prime to p. P is a prime number. This is just a product of a load of numbers less than p. So it's not divisible by p because p is a prime number. And so it can be cancelled. It's got a multiplicative inverse modulo p. So when we cancel that, what we see is that this power of n to the power of p minus 1 over 2, is congruent to minus 1 to the power of n. But we already know from Euler's criterion that that power of n to the power of p minus 1 over 2, is exactly the Legendre symbol. So that proves the result, that the Legendre symbol of n mod p is just this power of minus 1. So in other words, it tells you that the Legendre symbol np is equal to plus 1 if this number n is even, and minus 1 if this number n is odd. Remember, where this number n is what you see when you consider the congruence classes of all the multiples j times n, for every j from 1 to p minus 1 over 2, and you just count the number of times that it lands in the top half of the congruence class. You just get this count n. It's going to be odd or even. Okay. So this can be an alternative way of evaluating the Legendre symbol. It still requires you to do a lot of calculation to calculate, to carry out certain kind of operations p minus 1 over 2 times. You have to consider all of these p minus 1 over 2 multiples there. But whereas it might not be exactly an efficient computational tool, it does give very interesting kind of insights or way to get a hold on the structure of what's going on in the multiplicative system here. So you're looking at multiples of n, and you're tracking when they've broken through to the second half or whether they're still in the first half. And it's just another little incremental step on the way to being able to present a rigorous argument for the law of quadratic reciprocity. So we'll park that for the moment. We'll continue to develop on it next time, tomorrow perhaps. We may get to the final proof of quadratic reciprocity tomorrow. It'd be good to do that. But just to mix things up and not to have it all proof-based in one lecture, what I'm going to do next is go back to doing a practical application of quadratic reciprocity with one of our other special cases of Dirichlet's. Okay, so we discussed this a bit last time. Go forward to page 71. So as an introduction to this, page 71, we discussed this introduction last time. So Dirichlet's theorem, I won't spend ages discussing it. Again, I just want to get down to the actual exercise or application here. But Dirichlet's theorem is a generalization of the result we mainly attribute to Euclid that there's an infinite number of prime numbers. Okay? So Euclid's argument, which we saw in the very early days of this course, implied an infinite number of primes. Infinite number of primes in the integers. And this is like knowing the national anthem. Everybody has to know it. Just, if you want to be a mathematician, you have to know this argument. It's a proof by contradiction. You assume there's only a finite number of primes, P1 up to PR. Pretend that for a moment. You then consider the number m, which is multiplying all of them together. So that's a list. Here I'm talking about the product of them all. And you add 1. And then you consider prime factor q's. Okay, every integer does factor into primes. We know that already. So you consider the prime factors q of m, and you just investigate them. By assumption, they have to be one of the pi's. But that would imply then that the pi divides 1. Because if pi divides m, q is dividing m. If this pi divides m, pi obviously divides that product because it's one of the factors in it. Well, then pi is going to divide the difference, m minus that bracket. So pi divides as 1, and this is nonsense or contradiction. So the thing that went wrong there, we didn't prove nonsense. What went wrong is we made this assumption that there's only a finite, the list of primes ends. Okay, that is wrong. If you operate like that, you get nonsense. Okay, a contradiction. So that is not true. There's an infinite number of primes in integers. So you really need to boil that down to its essence and learn it, so to speak. So Dirichlet's argument, or Dirichlet's theorem, okay, I'm falling into introducing it all over again, but I just want to remind people of it. Dirichlet's theorem generalizes this. Okay. It says an infinite number of primes, not in the integers, but in the arithmetic sequence a plus nb, where n is in the integers. So you're not looking at every integer, you're only looking at the integers in the arithmetic sequence a plus n times b. Remember, this is the sequence that begins a, then a plus b, a plus 2b. So you're taking a step of distance b each time. And of course, it doesn't say there's an infinite number of primes in all of these, because there's a kind of a bit of a silly, it can't be true for all of them, okay? Because what if you choose, say, A to be 5 and B to be 10? Then your sequence will be 5, 15, 25, 35, 45, and it's plain for everybody to see that all of those numbers have a factor of 5. Okay? So you've chosen a 5 to start with, and the number you're adding on, 10, is itself a multiple of 5. So everything is going to be a multiple of 5. So those are silly choices if you want to generate primes. But as long as you rule those out, provided you ensure that the GCD of the two parameters A and B defining the arithmetic sequence is 1, that coprime. So it's not obviously the case that all of these elements are composite. As long as you rule that out, Dirichlet's theorem says there will be an infinite number of primes. And that kind of means that the primes are kind of fair and evenly distributed in the integers amongst the congruence classes modulo everything. Except that they have to avoid the obviously composite congruence classes, okay, the things that are not coprime to whatever modulus you're talking about. Here the modulus is B. We're talking about the sequence is the sequence of everything congruent to A modulo B. But apart from the obviously composite congruence classes, the primes are kind of, you'll find an infinite number of them wherever else you look. Okay? Remember, we're not claiming that all these numbers are prime. It certainly won't be, but you will always keep encountering more and more primes. Now, Dirichlet's, are any questions about the statement? Just appreciating the statement about what it says. Again, this points to, like, you can say this is a nice thing about the primes, that they're kind of evenly distributed everywhere we ought to find them. But that then kind of makes it, you know, that's also a source of their hardness as well. They aren't all found just in one place, they're kind of found everywhere. Even when you consider whatever modulus you want to consider, amongst the non-composite congruence classes, you'll always find an infinite number of primes. Now, Dirichlet's theorem itself, we can't prove with the tools we've developed so far, because it's just so general. It's, apart from this restriction on the parameters, the A and B, there's no other restriction, and it's just a bit too wide and general a result for us to get at. We need to develop so a bit more theory to deal with it. But what we can do is pick off various special cases of it. Various pairs A and B, specific pairs that we can prove it. Okay. So last time we saw the special case of 3 mod 4. Three modulo 4, or we actually tackled it as -1 modulo 4. 3 is congruent to -1 modulo 4. So today, what we're going to look at is exercise, just the next one. So it's page 72, 3-part B. There are an infinite number of primes of the form P equal to 8k plus 3, where k is an integer. What we're talking here is the congruence. What we're talking about is the congruence class of 3 modulo 8. We're not claiming that they are all prime, certainly not. 3, because the first 2 are primes. 3 is a prime, 11 is a prime, but then 14 isn't. 17 is a prime, but then 20. No, sorry, I'm adding 8 each time, sorry. 3 is a prime, 11 is a prime, add 8, 19 is prime, add 8, 27 isn't, add another 8, 35 isn't, add another 8, 43, 43 is. So some are prime, some are not. The Dirichlet's theorem, if we could prove it, would tell us there's an infinite number of primes there. But what we're going to do is we're going to just by focusing on this case, we'll be able to prove that there's an infinite number of primes. Okay? So it's not a general argument, it's specific. So here we got A equals 3 and B equals 8 in Dirichlet's. Now it's also inspired, or pretty much follows the structure of Euclid's argument for the infinite number of primes, okay? But in a slightly different way. Namely, that this pattern that you produce your large number with, where you multiply together all the primes and then add 1, that's going to be slightly different. Okay? Indeed, the necessary pattern is shown to you in the notes there. So here's the proof of it. It's a proof by contradiction, okay, which is a good proof technique. It gives you a strong assumption to start with, because you're assuming that the result is false. So if we assume that the result is false, that there's not an infinite number of primes, so that means there must be only a finite number. So a finite number of such primes. So in other words, primes that are congruent to 3 modulo 8. We'll call them P1, P2, up to PR. So they're all congruent to 3 mod 8. And there's a last one. So this is all of them. And it's not an obvious, we are allowed, you know, the assumption doesn't fall down itself as a contradiction straight away, because we know there are some primes of this form. 3 is a prime of this form, 11 is, 19 is. Okay? So there are primes of this form. So it's not obviously wrong to make that assumption. It will be wrong because it'll turn out that it is a contradiction, of course, as we want it to be. We want to see that it's a contradiction, so that we can then prove there's an infinite number of these primes. So we consider this number n. Now the correct pattern to use is given to us by the exercise. So we're multiplying together all these primes, P1 up to PR, just as we did in Euclid's argument. This time we're not adding 1, we're adding 2. And before we're adding 2, we're squaring that product. Now the reason for squaring it will allow us to talk about quadratic residues. Okay. Sorry, can we just keep the chatter down a bit, please? It's quite obvious. Thanks. The fact we're bringing squaring in means we're kind of adding quadratic residues into the mix. Okay. We're throwing in that concept of squaring, and so with what we built up about quadratic residues, this will hopefully allow us to gain some insight into this case. Okay. The proof we did last time of primes of the form 4n minus 1, we didn't need anything to do with quadratic residues for that. For that, we were just able to do a straight imitation of this proof, and it worked out. But for primes congruent to 3 mod 8, just a straight imitation of that proof isn't enough. We need a bit more. Okay. So n certainly has prime factors, because every integer does. You know that. Consider such a factor q. It's a prime factor q. Q divides n. So in other words, q divides this number, which is the product of all the p's squared plus 2. So what is this saying about the quadratic residues? Remember, we're striving for a contradiction out of this. So this is saying to us that so q divides this number plus 2. That means that minus 2 is congruent to this number modulo q. Okay, this is exactly the definition of congruence. X is congruent to y means the modulus q divides the difference x minus 1. So here we got this squared bracket plus 2, so that means that minus 2 and the squared bracket are congruent to each other modulo q. So in other words, that's saying that minus 2 is the square of something modulo q. So minus 2 is a quadratic residue modulo q. So that implies that the Legendre symbol is plus 1. Q is a quadratic residue. Mod q. Sorry, it's minus 2 is a quadratic residue. Modulo 2. Now, we haven't proved a result about minus 2, about the Legendre symbol values of minus 2, but we have proved one about 2. See, it's up here on the board. And we've also proved one about minus 1, which we proved before we did this. One about minus 1, put that on the board, is that minus the Legendre symbol of minus 1 mod p was plus 1 if p was congruent to 1 modulo 4, and minus 1 if p was congruent to 3 mod 4. I believe it's from my memory, but that was it. Yes. Okay. So we know about Legendre values of 2 and minus 1. Here we got minus 2, but we also know that the Legendre symbol is multiplicative. So this Legendre symbol we can factorize as the product of these two. Yeah? So that tells us this Q that we have, it satisfies this. Now this is telling us, so here we've got the product of two Legendre symbols. Each one on its own is equal to plus or minus 1, remember? And when you multiply them together, you have plus 1. So that means what's going on here is one of two cases. Either these are both plus 1, or they're both minus 1. Yeah? It couldn't be that one of them is plus 1, the other one's minus 1, because then their product would be minus 1. Right? So they're either both positive, plus 1, or they're both negative, to give you a product of plus 1. So that implies we've got two cases. That minus 1 mod q is equal to 2 mod q and is equal to plus 1, or minus 1 mod q, the Legendre symbol is equal to the Legendre symbol of 2q is equal to minus 1. One of these two things must be true. But we completely understand the conditions that all these values occur because we've proved results about Legendre symbol 2 modulo anything and Legendre symbol of -1 modulo anything. Okay, so we just need to bring these results in now. So our top line case happens, so when is -1 modulo q equals +1? It's when q is congruent to 1 modulo 4. And the second, when is 2q equal to +1? 2q will be equal to +1 when q is plus or minus, listen from there, it's plus or minus 1 modulo 8. And the second line happens, so -1 is -1 when q is 3 mod 4. And the 2q is -1 when q is plus or minus 3 mod 8. Okay, everybody happy with that? Remember, this is properties that the prime factor q of this new number, new integer n that we formed will satisfy. Now, congruence class mod 4 and congruence class mod 8 are fairly easy to combine statements about because 4 is half of 8. 4 divides 8. So how can it be that q is congruent to 1 mod 4 and it's also plus or minus 1 mod 8? Remember, plus or minus 1 mod 8, another way of saying that is 1 or 7 mod 8. Well, q has to be 1 mod 4, but can it be 7 mod 8? Because if you were congruent to 7 mod 8, that means you're 8 times something plus 7. But how does that divide by 4? Well, the 8 times something is divisible by 4. And then when you divide the 7 by 4, you get remainder 3. So being congruent to 7 mod 8 is incompatible with being congruent to 1 mod 4. Okay, so the only way that this whole conjunction and can be satisfied is if q is only congruent to 1 mod 4. Okay, can't be congruent to 7 mod 8. Remember, the 7 mod 8 is coming from the separate condition that 2q is equal to +1. But 7 mod 8 is 3 mod 4. So it must be that q is congruent to 1 mod 4. Sorry, 1 mod 8. Okay, 1 mod 4 is always 1 mod 8. It must be congruent to 1 mod 8. Okay, everything that's congruent to 1 mod 8 is congruent to 1 mod 4. The second condition says maybe q is plus or minus 3 mod 4. Remember, plus or minus 3 mod 8. Plus or minus 3 mod 8 is also 3 or 5 mod 8. Now, if you're 3 mod 8, yes, you're congruent to 3 mod 4. But if you're 5 mod 8, you're congruent to 1 mod 4. So the 5 mod 8 is impossible in this case because it's paired together with the 3 mod 4, which is coming from the -1 q equals -1. Okay. So it can't be congruent to 5 mod 8, so it must be congruent to 3 mod. There's still an or between these two lines. So where were we for a second? So summary, where we got, if n is this number, the product of all, wrongly assuming all of the primes congruent to 3 mod 8, that's all of them there, we've assumed, we squared them, we've added 2. Q is a factor, q divides n, that implies q is plus or minus, 1 or 3 mod 8. That's a summary of what we've just done. I shouldn't write if implies, I should write if then. So n is this number. If q divides n prime, then q is congruent to 1 or 3 mod 8. What is, so we're studying factors q of n modulo 8, but what is n mod 8? See, all these primes are congruent to 3 mod 8. But we're squaring them all. And when you square 3 mod 8, you get 9, which is 1 mod 8. So you square each of these primes, you get 1 mod 8. You multiply them together, you get 1 mod 8. So you're multiplying together a lot of 1s. Then you add 2. So actually, n is congruent to p1 squared, p2 squared, pr squared plus 2. This is congruent to 3 squared, a load of 3 squareds plus 2. These are all mod 8, mod 8. So that's congruent to 3 mod 8. These squared 3's all come to 1, then you're adding 2. So n is congruent to 3 mod 8, and any prime factor it has must be congruent to 1 or 3 mod 8. Can we say that a definite, remember we're trying to prove an infinite number of primes congruent to 3 mod 8. Can we say that n definitely has at least one prime factor congruent to 3 mod 8? If that failed to happen, if it was only true that prime factors q of n were congruent to 1 mod 8, remember n is the product of all its primes. So if it was only the case that prime factors of n were only congruent to 1, then n would be congruent to 1 mod 8. Okay? Because an integer is the product of its prime factors. So if all the prime factors of n were congruent to 1 mod 8, so would n be. But by construction, n is congruent to 3 mod 8. So n, there must be some prime factors congruent to 3 mod 8. So that implies there exists a q such that q divides n and q is congruent to 3 mod 8. Well, by assumption, it must be one of the p's. Okay? Because we've assumed, wrongly, but for the purposes of proof by contradiction, we've assumed that there are only a finite number of such primes congruent to 3 mod 8. And we have them all there, p1 and pr. So that implies that q is equal to one of the pi's. But then you force out the contradiction just like we did in the example. If q is one of these primes here, and q is also dividing n, this is going to imply that q divides 2. Okay, because q is dividing this part here, q is dividing this part here, because it's one of the pi's, therefore it must divide 2. But that is just a nonsense statement. This is a contradiction. 2 only has one prime factor, namely itself 2, and that is not congruent to 3 mod 8. Q is congruent to 3 mod 8. Okay. So this contradiction we've apparently discovered. If you do ever discover a contradiction, better run and hide, because everything's going to end. But so what went wrong? What went wrong is our very, very first statement. We assumed there was only a finite number of these things. Okay, that's what produced the contradiction. We know there are some of these things because 3 and 11 are some primes of congruent to 3 mod 8. There can't be a finite number of them, so there must be an infinite. So there are an infinite number. Edward. Okay, so there are an infinite number of such primes. Okay, so before the next session, so we're going to see you again tomorrow, it'll be a good exercise for you. See, there's one more of these examples. There aren't many of these examples, specific cases of Dirichlet's theorem that we can prove relatively straightforwardly like this. But there's another one given here, which are the primes congruent to 1 modulo 6. You're given the pattern here to use. Again, you can see the squaring involved. So it's not surprising that that's going to require talk about quadratic residues in a somewhat similar way to the way we talked about it here. So please give that a try before tomorrow afternoon, and we'll examine the argument for it tomorrow afternoon. Okay.